Hi, we are going to talk about integration by parts, but there is a shortcut that you can use which is called the tabular method, which allows you to make it faster and not as quite tedious as sometimes it can get, especially when you have to apply it more than once. So we're going to start with this problem. This is a pretty basic problem. This is how it's going to work. Instead of setting all these up through integration by parts, we're going to make a table. This is how I usually make that. So this is the column for derivative. This is the column for integration. So you're going to break it up out of x and sin x. One of them is going to go in one and the other one's going to go in the other. So what can we do here? When you have anything that's like polynomial, in this case it's x, I know it's linear, but it's a type of a polynomial. These things can generally be you usually put them in the differentiation column, and I will explain in a moment why. And here we're going to put the other part of that expression, which is sin x. And here's what we're going to do. We're going to start differentiating. The first thing, when you differentiate x, you're going to get 1. And when you differentiate 1, you're going to get 0. 0 is ideal for us because it makes things very nice, but it's not always going to happen. And then what happens here? So you integrate sine x. The integral of sine x is negative cosine x. The integral of negative cosine x is going to be negative sine x. This is how you're going to proceed from here. So first of all, you're going to need to put the signs there. So the signs will always start with a plus, and then minus, and then plus, and you just, for as long as you need to, you continue alternating them. And then what you're also going to do is you're going to go diagonally, kind of like this. The only thing where you don't go diagonally is on the very bottom. The nice thing with the 0, if you get 0, and you are multiplying this, when you multiply 0 by anything, you get 0, then you don't need to worry about any integrals. So what are we getting here? We have x times negative cosine x minus 1 times negative sine x. Again, since we have 0 in our last column, last row for the product, we do not have another integral. We can just write plus c, and we're just going to rewrite that in a nicer way, which is negative x cosine x plus sine x plus c. If you saw my previous video on integration by parts, you will notice this is actually the first example that I did there, and it's exactly the same answer. Alright, so let's go ahead and take a look at another example. So this example here is x cubed times sine x. Here's a problem if you want to use just integration by parts. Because of that being x cubed, you're going to have to use integration by parts 3 times. And that's going to become quite challenging. So let's see how it's going to work with a tabular method. This is a polynomial, so we are going to put that into the differentiation column. The reason we always put polynomials in differentiation columns is because this is where you are going to get eventually 0. Because as you continue integrating, no matter how high the degree you're going to start with, you're always going to reduce it to 0. So the derivative of x cubed is 3x squared. Derivative of 3x squared is 6x. Derivative of 6x is 6. Derivative of 6 is 0. Once we reach 0, we are very happy. Let me do the integration column. So obviously here you're going to get sine x. Just be careful when you integrate that. So the first thing is going to be, when you integrate sine x, you get negative cosine x. When you integrate negative cosine x, you get negative sine x. When you integrate negative sine x, you're going to get cosine x. When you integrate cosine x, you get sine x. And just like we did with the previous problem, we are going to start with the plus, then the minus, then the plus, then the minus, then the plus. It's really irrelevant for 0, but it's not always going to be 0. You are going to see that example. And we're going diagonally, except the last row. Okay, so now we can rewrite the whole thing. So the first thing is positive x cubed times negative cosine x. Then we're going to have minus 3x squared times negative sine x plus 6x times cosine x minus 6 times sine x, and 0 here indicates that the whole thing is going to be 0 and you do not need anything else here. Let's just rewrite that in a nicer form. So it's going to be negative x cubed cosine x plus 3x squared sine x plus 6x cosine x minus 6 sine x, and of course plus c. I should have put plus c here as well. All right, that is going to be the answer here. Okay, just imagine doing this if you wanted to do integration by parts. You're gonna have to do that process 3 times, and each time you're gonna apply that process, you can possibly make a simple mistake, like with a sign, and get it all wrong as a result of it. Okay, so let's go ahead and take a look at the next problem. So you got x cubed ln x. This is our other problem. So what are we going to do here? Well, since we don't really know how to integrate ln x, then our differentiation column is going to have ln x, because we know how to differentiate that. And then x cubed is going to be here, and we're going to integrate that. So this one's going to be a little different. And you will see in a moment what's going to happen here. So the derivative of ln x is going to be 1 over x. The integral of x cubed is going to be x to the 4th over 4. The problem is, if you continue differentiating here, you will never get 0, because the next derivative is going to be negative 1 over x squared, etc., etc. If you flip them, you're going to run into a problem. You need to know what the integral of ln x is, and we're working under an assumption that you don't know. So we're not going to get 0 here. But we're going to stop here, and I will explain to you in a moment why. So, this is plus minus. So we're going to go down here, we're going to go horizontally. But because it's not 0 in the last row, you will need an integral. So this is what your problem is going to look like now. So it's going to be ln x times x to the 4th over 4, and then we're going to do minus, and then you're going to have an integral, this minus here, and then it's going to be 1 over x times x to the 4th over 4 dx. So this is what I was mentioning earlier when I was explaining that there is 0 for the other two problems, but here you do not have 0. So no 0 here indicates that the last row is going to give you a product that's going to go under an integral sign. And then you integrate that, and hopefully that's going to be in the way that you should be able to do it. So ln x times x to the 4th over 4 minus the integral of x cubed over 4 dx, and that's going to give us x to the 4th over 4 ln x minus x to the 4th over 16 and plus c. Okay. Let's take a look at a couple more. So how do you do that with ln x? Just ln x. So the derivative and the integral, just like we already had a problem where ln was used, so ln x goes into differentiation column. So we don't have anything for integration, we're just going to put 1 there. And then here we're going to end up getting 1 over x, and when you integrate 1, you're going to get x. We know we're never going to get 0, so we are going to stop here. Plus minus. Like this and like that. We do not have 0 in the last row, so we are actually going to have an integral in our next step. So this is going to be ln x times x minus the integral of the product of these two things, 1 over x times x dx. So this is going to be x ln x minus integral of 1 dx and that's going to be x ln x minus x plus c. Alright, I do have one more problem to show you. This is a problem where you are actually never going to be able to completely rewrite that, but you will see something interesting that can happen. So we're trying to integrate e to the x sine x. As you know, both of these functions, e to the x, if you continue integrating or differentiating that, you continue getting e to the x. With sine x, as you continue integrating or differentiating that, you're going to continue getting sine x, cosine x with pluses and minuses. So let's set it up and let's see how it's going to work. So we're going to put e to the x here. You can do it the other way here, by the way. Sine x. So the derivative of e to the x is e to the x. The derivative of e to the x again is e to the x. The derivative of, the integral of sine x is negative cosine x. The integral of negative cosine x is negative sine x. I'm actually going to stop here. You will see what's going to happen in a moment. See, the thing here is we still never really got rid of either one of them. We still have e to the x and we still have either sine or cosine. But you will see something interesting in just a few seconds. So we can rewrite our integral, but I'm going to have to copy this original problem here. So integral of e to the x sine x dx, according to this, is going to be e to the x times negative cosine x, which is negative e to the x cosine x, minus the product of e to the x times negative sine x, which will give you plus e to the x sine x. And then this is going to give us the integral, because that's when we just go horizontally. There's going to be plus and the negative, so minus the integral of e to the x sine x dx. And here's an interesting thing. You see those two things? They are identical. So what we can do is we can take this one here. Well, but basically we can add the integral of this on both sides. And when you do that, you are going to be careful they do not cancel. 2 times the integral of e to the x sine x dx is going to equal to all the other remaining stuff. Minus e to the x cosine x plus e to the x sine x plus some arbitrary c1. And we want this without the 2. So we divide both sides by 2. And you will actually have your answer. So integral of e to the x sine x dx is going to equal to negative 1/2 e to the x cosine x plus 1/2 e to the x sine x plus, and we're dividing c1 by 2, and let's just call that value c, and this is our answer. So using a tabular method here is a very powerful tool for a problem like that, where we can't really completely get rid of that, nor simplify it in any significant way, but we can get that to the point that the integral that's going to be remaining here is going to match the original integral. So this is how it works, and I hope this helps. I'll see you next time.